Assalamualaikum and good day everyone. We are Group 1 and today we will present our industrial best cam project for BMIM 2123 multi-axis machining. Our project focus on developing a complete CAD cam workflow for manufacturing a curved guide block using CATIA V5. I will introduce my name and my group member. My name is Muhammad Alif bin Muhammad Azizi. Cakap nama apa?
My name is Muhammad Izan Safwan.
My name is Muhammad Danish bin Rizal.
And my name is Muhammad Aminul Aiman bin Zainuddin.
Okay. This is our introduction. The curve guide block is a mechanical component really used in motion control system, sliding mechanism and industrial automotive application. Its primary function is to guide movement along a predefined curve path while ensuring stability, smooth motion and proper load distribution. Due to its functional requirement, the component typically involve complex curve geometry and precise surface transition which demand high machining and accuracy. Next. This is our tool listing. Tool number 1, we use face mill, diameter 15 mm and operation facing. Second tool, end mill, diameter 8 mm, operation roughing. And tool number 3 is end mill, diameter 5 mm, we use for profiling, flank and finishing. T number 4 is ball nose end mill, diameter 7 mm, we use operation for multi-axis sweeping. And last, T number 5, we use tool end mill, diameter 4 mm and operation for pocket. Okay.
Thank you, Presenter 1. Now, I will explain the CAD model and machining setup. First, the curve guide block was designed using CATIA V5 part design. Since this component contains complex curve surface, it requires multi-axis machining to achieve better dimensional accuracy and surface quality. Next, we define the stock material as an aluminium rectangular block. Then, we establish the work coordinate system WCS to ensure proper alignment between the workpiece and the CNC machining during simulation. After completing the setup, we selected the cutting tool for each machining operation. We use a 50 mm face mill for facing, 5 mm end mill for profiling, flank, contouring and finishing, 7 mm ball nose end mill for multi-axis sweeping, and finally a 4 mm end mill for pocketing. Each cutting for was selected according to its machining function to achieve efficiency, metal removal, good dimensional accuracy, and excellent surface quality. The first machining operation is facing, which use the 50 mm face mill. The purpose of this operation is to remove the uneven surface of the raw material and create a flat reference. Before the remaining machining process begin. After the facing operation was completed, the workpiece had a smooth and flat top surface providing a suitable reference for the next machining operation. Now, I would like to hand over the presentation to presenter 3.
Thank you, Aiman, as presented too. So next, I will explain the main machining operations we use to perform in this project. So the first operation in this section is roughing, which uses an 8 mm end mill. The objective of roughing is to remove most of the excess materials as quick as possible while leaving a small amount of material for finishing operations. This helps reduce the total machining time. Next, profiling, and finishing. We refine the component geometry after roughing. This operation improves dimensional accuracy and produce a smoother surface finishing by using smaller cutting steps. One of the most important operations in multi-axis flank contouring is in the process, the cutting tool continuously changes the orientation while following the curved surface of the component. Compared to conventional machining, this strategy provides better geometry accuracy, smoother surface transition, and reduced scallop height. The simulation also confirmed that the tool followed the program toolpath smoothly without any collision during the flank contouring process. Now, I would like to invite presenter 4 to continue with the remaining machining operations and the project conclusions.
Thank you, presenter 3, Danish. Now I will continue with the multi-axis sweeping, pocketing, and conclusion. The next operation is multi-axis sweeping, which is use 7 mm ball nose and mill. This operation is used to machine the free-form curved surface of the curved guide block. The rounded tip of the ball nose and mill allows smooth tool movement across the curved geometry, producing is a better surface finish and reducing scallop marks. The final machining operation is pocketing, which is use a 4 mm end mill. Pocketing removes material from internal cavities and narrow areas that cannot be reached by larger cutting tools. This operation ensures that the final geometry meets the required design specification. After completing all machining operations, we review the machining simulation in CATIA V5. The simulation confirmed that all tool paths were successfully generated with smooth tool movement and no machining error. The final machining component closely matched the original CAD model. In conclusion, this project successfully demonstrates a complete CAD/CAM workflow using a CATIA V5 from 3D modeling to multi-axis machining simulation. By applying different machining strategies such as spacing, roughing, profiling, flank countering, sweeping, and pocketing, we achieve efficient material removal, high machining accuracy, and excellent surface quality. This project also proved that multi-axis machining is highly effective for manufacturing components with complex curve geometry while improving productivity, ensuring safe CNC machining operation. Thank you for your attention. That's all from us. Thank you.
Thank you.
Thank you.